Okay, this is the video accompanying lecture 2 for Math 31 AH. And so let me just write that down. So this is lecture 2. And the one of the main things that happened in lecture 2 is a kind of a key result. Okay, so key result, which is very important in linear algebra, and it's the following. So I believe this is stated as theorem 1 in lecture 2. I'll just call it theorem here without numbering it. And the theorem says is that for a vector space V, the following are equivalent. Okay, so there are two logical statements that actually their truth is equivalent to one another. And the first of those is that the dimension of this vector space V is equal to some non-negative integer n. Okay, and 2, which is equivalent to statement 1, is that V contains a basis B, right, consisting of some vectors and in fact n of them. Right, so a basis B equals B1 through Bn of size n. Right, and that's a very important result. And one of the main features of this result is that it actually gives you a method to calculate the dimension of vector spaces. All right, so calculating the dimension of vector spaces directly from the definition is kind of hard, right? So what do you have to do to show that the dimension of the given vector space is n? Just working from the definition, you have to show that it contains a linearly independent set of size n, and then you have to show that it doesn't contain a linearly independent set of size bigger than n. And so condition 2 here, property 2, kind of really takes away the effort that you have to do for the second part of that check, and bundles it into this really hard lemma that's proved as lemma 1 in the lecture notes, and that you can now just use. And so so the method could be summarized as follows. So to calculate the dimension of a given vector space V, find a basis of V. Right, so that means that if you're handed some vector space and you want to figure out what its dimension is, one possible way to proceed is to try to find a basis in that vector space. So in other words, a linearly independent subset of the vector space V, which spans V, meaning that every vector can be written as a linear combination of basis vectors, in fact, in a unique way, as was proved in lecture 1. And then you just count the number of items in that basis that you found, and that is the dimension of V. And so this technique brings one of the homework problems kind of into range, and so that is problem 2. All right, so problem 2 consists of 2 parts. So this is problem 2a, and it what does it ask? It says something like show that the vector space of polynomials of degree at most 4, at most, is that what it says? Or maybe it says, I forget what number is chosen. At most 4 is 5-dimensional. Or it says something like this. Close enough, all right? So how would you solve something like this? So let's first just make sure we know what kind of space we're talking about. So what does V look like? So this is the set of all polynomials of degree at most 4. So these are things that look like a0 plus a1 x to the 1 plus a2 x to the 2 plus a3 x to the 3. Okay, I don't want to write too much. I'm going to change this to 3, and I'll change this to 4. A3x to the 3. Okay, such that, okay, so x is a variable here, and a0, a1, a2, a3 are numbers, real numbers, which are referred to as the coefficients of this polynomial, right? So this is a polynomial of degree at most 3. Why is it degree at most 3? Because a3 could be 0. That's possible, which would mean that the degree of this polynomial is something strictly less than 3, right? And a0, a1, a2, a3 can be any numbers that you want. Okay, and so let's just briefly recap this vector space of polynomials. So suppose I have a polynomial p of x is equal to, let me just use the same notation. So a0 plus a1x plus a2x squared plus a3x to the power of 3. And another polynomial, let me call it q of x, which is b0 plus b1x plus b2x squared plus b3 x cubed. So how is vector addition defined in this vector space? What does it mean to add two polynomials together? Well, what it means is that this is the definition of adding two polynomials. You add up the coefficients of like powers. So this would be a0 plus b0, right? Those are the coefficients of the degree 0 term, which actually you could write like this if you want. Right, so x to the power 0 is 1, plus the sum of the coefficients of the degree 1 term, right, x to the 1, plus the sum of the coefficients of the degree 2 terms, so a2, b2, x squared, and then finally the sum of the coefficients of the degree 3 terms, so x cubed. Okay, so that's what adding up polynomials means. And what about scalar multiplication of polynomials? So suppose that I multiply my polynomial p of x by some number t, right? So t, this is a real number, an element of the real numbers. So t times p of x, by definition, just means multiply each of its coefficients by the number, by the number t, right? And that gives you a new polynomial. So ta0 plus ta1 x to the power 1 plus ta2 x to the power 2 plus ta3 x to the power 3. Okay, and you probably also know that you can multiply polynomials together, right? You can also multiply polynomials together. You can write p of x times q of x. So what is that? That's a0 plus a1x plus a2x squared plus a3x cubed times b0 plus b1x plus b2x squared plus b3x cubed. And how do you evaluate this product? Well, what you do is you multiply out the brackets and then you collect together like powers of x. So even though it is possible to multiply polynomials together, we're not going to do that here, right? So we're thinking of polynomials as vectors in a vector space, and in a vector space, all that you think about is adding and scalar multiplying. So even though it's true that this is a special type of vector space where you can multiply vectors together, that's not going to play any role in the considerations that we are going to pursue. Okay, and so let's see if we can calculate the dimension of this vector space V. So what do I need to do to calculate the dimension of V? I need to, so let me copy it down. That's up here. Let me grab this thing, copy it. All right. Okay, so in order to calculate the dimension of V, all right, so it suffices to find a basis of V. Okay, and I suspect that it's probably pretty clear to most everyone what that basis is, right? So I'm looking for a subset of V which spans the vector space V. So here's a set of polynomials that spans V, right? Let's x to the 0, which is the same thing as 1, x to the 1, x to the 2, x to the 3, right? So those are vectors in V, right? They're polynomials in the variable x, and there are 4 of them, and they definitely span V, right? In fact, that's sort of the definition of what polynomials of degree at most 3 are. They're linear combinations of these 4 monomials, right? X to the power 0, x to the power 1, x squared, and x cubed. And so definitely V span, sorry, other way around. B spans V, and this is really by the definition of a polynomial in X. Okay, a polynomial of degree at most 3. Okay, but there's still one more thing that we need to do. We need to show that B is linearly independent. All right, and so how do we do that? So let me, so what does that mean? Okay, so first of all, what does that mean? So this means we need to prove that if a0 times x to the 0 plus a1 times x to the 1 plus a2 times x squared plus a3 times x cubed is equal to the 0 vector in my vector space V, then all these numbers, all these coefficients, these scalars, are equal to the number 0. Okay, so that's what is required to be done in order to show that B is a linearly independent set. Okay, so let me drag that over to the next page. All right. So why is this the case? This is the case because in the vector space V, the 0 vector is the polynomial. What is it? It's the polynomial all of whose coefficients are 0. So the 0 polynomial is 0 times x to the 0, the number 0, plus 0 times x to the 1, plus 0 times x to the 2, plus 0 times x to the 3. Okay, and so that's the 0 vector in this vector space of polynomials of degree at most 3. And what would it mean for a0? Let me keep this x to the power 0. What would it mean for this polynomial? Right, so this is a linear combination, an arbitrary linear combination of the monomials x to the 0, x to the 1, x to the 2, x to the 3, what does it mean for this to be equal to the 0 polynomial, right? So 0x to the 0 plus 0x to the 1 plus 0x to the 2 plus 0x to the 3, right? So what does it mean for two polynomials to be equal? It means exactly that their coefficients are equal. That is the definition of two polynomials being equal. So this equation holds true if and only if a0 is equal to 0, right? So the coefficient of the x to the 0 term on both sides is the same, all right? And a1 is equal to 0, and a2 is equal to 0, and a3 is equal to 0. And in other words, there's no way that you can take the monomials x to the 0, x to the 1, x squared, and x cubed, and add them up with scalar multiples to get the 0 polynomial unless all of the scalars you use to generate this linear combination are the number 0. Okay, so this means that B is linearly independent, and in particular is a basis, since we already know that it spans V. Okay, so we can conclude that since the size of the set B, which is often written like this, absolute value of B is equal to 4, sometimes pronounced the cardinality of B is 4, then the dimension of V is also equal to 4. Okay, and that's it really. And so that's an example of using this theorem on the connection between size of basis and dimension of the vector space containing that basis in order to actually compute the vector space dimension of some given space. Okay, and now what about part B? Okay, so this is question 2B. It says, so let V be the space of all polynomials in the variable x. Okay, prove that V is infinite dimensional. All right, so how do we do that? Well, as a first step, let's check that we can actually write down what V is. Okay, so what is V, right? So V, if I wanted to write this down in a concise way, this is the set of all polynomials of arbitrary degree. So this looks like a0 x to the 0 plus a1 x to the 1 plus all the way up to m x to the m, where m can be any non-negative integer, all right? And the coefficients a0, a1, up to am can be any real numbers. All right, so that's this vector space V. And you can see that it's much bigger than the vector space from the previous question, where this m was capped, right? It was not allowed to go above the number m equals 3. And here it's not, it's unbounded. So this is definitely a much bigger object. And in fact, it is an infinite dimensional vector space. Okay, that's not working out for me, so let me just skip that. Okay, so how do you prove that this is infinite dimensional? So we're required to show, so you have to just use the definition of what it means for a vector space to be infinite dimensional. And what that means is to show that V contains linearly independent sets which can be arbitrarily large, right? required to show, so how do you write that down more precisely, that for any number n, okay, any number n, 1, 2, 3, 4, as large as you want. So this is the set of natural numbers. V contains a linearly independent set Bn of size n, right? So V contains linearly independent sets of size 1, of size 100, of size 1000, of size 1 million, size 1 trillion, so on. Okay, as large as you want. And so how do we do that? What did we do in part A? In part A, we showed that that B4, okay, equal to x to the 0, x to the 1, x to the 2, x to the 3 is a linearly independent set. In particular, of size 4. And that's pretty suggestive, right? So this sort of says that you can probably kind of see how to get a linearly independent set of size 5 or 6 or 600 million. And it's pretty clear how to just change this number 4 into whatever I want it to be. And so I think I will leave that up to you to write down the details, and we will discuss the remaining problems in the problem set when we meet on Friday for our flipped classroom session.